There are distributions that are encountered very often in mathematical models that describe typical situations, typical events that happen in our life. And these distributions have their own names. We know their properties, we know formulas for their expected values, variances, CDFs, PDFs, just not to invent the wheel every time we meet such a situation, we find such a model, but to use these formulas just to apply them. And so now we will discuss several distributions that are the most typical, that are encountered very often. And so we will discuss their physical meaning, the situations in which we can find these distributions. And the first one is a binomial distribution. Binomial distribution can be defined as a number of successes in a series of Bernoulli trials. So you have a series of Bernoulli trials. Let me remind you what a series of Bernoulli trials is. So you have a trial with two possible outcomes that are called a success and a failure. And so this trial is repeated several times, and two conditions are to be met. The first one is that trials are independent from each other. So the outcome of each trial does not affect anyhow outcomes of the other trials. And the second condition is that probabilities of the success and the failure are to be constant. So they do not change during this series of trials. And so you have a series of Bernoulli trials, and so you see that number of successes is a random variable. So, for example, number of heads in 5 flippings of a coin. It can take values 0, 1, 2, 3, 4, 5. It has 6 possible values, and so this is unpredictable. Every time you do these 5 flippings, you get some of these 6 numbers. So so that means that this is a random variable. And the distribution of a random variable of this kind is called a binomial distribution. So, and we say not simply binomial distribution, but binomial with parameters n and p. And n is the number of trials, and p is a probability of success in each single trial. So these typical distributions have their own symbols. And for binomial distribution, this symbol is b. So you should understand that this is not a function. So this b and n and p in brackets, this is not a function of 2 arguments. This is just a symbol. So not to write binomial distribution with parameters n and p, they usually use this short symbol for this distribution. And tilde means distributed. So this formula can be read as x is distributed according to binomial distribution with parameters n and p. So tilde is for distributed, and this sign b is for binomial distribution. And we have formulas for PMF, so for probability of taking some particular value. So if k is a value from 0 to n, probability that x will take this value is n choose k times p power k times 1 minus p power n minus k. So this is the Bernoulli formula. You already know this formula. And formulas for the expected value and the variance are np and n times p times 1 minus p. So these formulas can be found just using definitions of the expected value and the variance. So now let's discuss a couple of examples where we use a binomial distribution. Usually in some problems that you are solving on your exams and so on, all distributions that are given are usually named. So you are told that x follows exponential distribution or normal distribution or uniform distribution. All distributions are named except for the binomial one. So when you are dealing with a binomial distribution, the first step is to understand that the distribution is actually a binomial one. So how to do this? So when the random variable of your interest is a number of successes in a series of Bernoulli trials, if it is equal to a number of successes in a series of Bernoulli trials, that means that this is a binomially distributed random variable. So let's consider the first example, this simple one. Let's say that x is a number of heads in 7 flippings of a coin. So, and they ask us to find expected value of x, variance of x, and probability that x is somewhere between, let's say, -1 and 3.5. So, as you see, they don't say anything about the distribution. They say x is a number of heads in 7 flippings of a coin. So, but you say that flipping of a coin, multiple flipping of a coin, is a classical example of what the Bernoulli scheme is, what a series of Bernoulli trials is. So you say this is a number of successes in a series of Bernoulli trials. Each flipping is a trial and heads is a success. So number of trials is 7 and probability of success is 1/2. We suppose that this is a fair coin. So you say that x has the binomial distribution with parameters 7 and 1/2. And after you know this, everything else is just very simple because you use formulas that are ready, that are waiting for you to use them. So as for the expected value, you say that expected value is n times p, that is in your case 7 times 1/2, that is 3.5. So average value of heads when the coin is flipped 7 times. Then variance. For variance of a binomially distributed random variable, you also have got a formula n times p times 1 minus p. So this means 7 times 1/2 times 1 minus 1/2, that is 1/2 also. And so this is 1.5 0.75. So this is the variance. And as for the probability, you say that number of heads in 7 flippings can take values 0, 1, 2, 3, 4, 5, 6, 7. So which of these values are in this range between -1 and 3.5? So 0, 1, 2, and 3. 4 values. So probability, this probability is actually sum of probabilities. So probability that x is 0 plus probability that x is 1 plus probability that x is 2 plus probability that x is 3. So let me remind the Bernoulli formula. Probability that x is equal to k can be found as n choose k, but our n is 7, so 7 choose k, times p to the power of k, our p is 1/2, so 1/2 to the power of k, times 1 minus p to the power of n minus k, so 1 minus 1/2 to the power of 7 minus k. So you see that in our particular case, this is 1/2 and this is also 1/2. And so every time here we have just 1/2 to the power of 7. So in our case, we have 7 choose k times 1 divided by 2 to the power of 7. And so to find these probabilities, you are to substitute 0, 1, 2, and 3 for k here in this formula. And then you will find these 4 probabilities and you will add them and you will get the final answer. Let this be your task to find the final probability in this example. So another example. Let's say that 40% of all people who live in Moscow were born outside of the city. And let x be the number of people born not in Moscow out of 3 random people you meet, let's say simply at the street. So here we have nothing else but a series of Bernoulli trials. So we have a series of 3 trials. Each trial is a situation when you ask a person where they were born and they answer, so in Moscow or not in Moscow. So, and when they say not in Moscow, this is a success. So, and X is a number of successes in a series of 3 Bernoulli trials. So X follows binomial distribution with parameters 3, and the second parameter is 0.4, as we know that 40% of all Muscovites are actually were born outside of the city. So I haven't yet said what we are going to find here. So let's say that we are asked to find the expected value, the standard deviation, and value of the CDF. It's in some point, let it be 1.2. So as for the expected value and the standard deviation, we just do what we have already done in previous example. So we say that expected value is n times p, or 3 times 0.4, that is 1.2. So sigma, standard deviation, is square root of variance, and variance is n times p times 1 minus p. So in our case, this is 3 times 0.4 times 0.6, and this is equal to, this is approximately 0.849. So, and as for the CDF, actually we don't need to find the general formula for the CDF. We just need to know the definition. Know the definition of what the CDF is. And let me remind you. So the CDF is a function that is equal to the probability that x is less or equal than small x. So in our case, small x is 1.2. So x, what values x can take? 0, 1, and 2, and 3. So which of them are less than 1.2? So 0 and 1. So this is probability that x is 0 plus probability that x is 1. And these two can be found with the Bernoulli formula. So formally, in this case, we have 3 choose 0 times 0.4 to the power of 0 times 0.6 to the power of 3. Actually, this is 1, and this is also 1. This is 3 choose 0 is number of ways to choose nothing out of 3. So there is only one way to choose nothing, not to choose anything. Just so that is why this is 1. You can simplify this by yourself. So you can write down all these factorials, and you will see that this is 1. This is also 1 because of the 0 power, and here we have 3 choose 1 times 0.4 power 1 times 0.6 power 2. So 3 choose 1 is 3. So how many choices are when we are choosing 1 out of 3? 3 choices. So this is 3, this is 0.4. 3 times 0.4 is 1.2. So we have and if we count this, it is 0.936. So very close to 1. So with high probability, this value of x will be 0 or 1, not 2 or 3. So we have found everything we were asked to find. So we know expected value, standard deviation, and the value of the CDF at a given point. Another distribution based on this concept of the Bernoulli trials is a geometric distribution. Geometric distribution is a distribution of a random number of Bernoulli trials needed to get one success. So number of trials before we get the first success in our series. And so before the success and this successful trial itself also. So the symbol of geometric distribution is letter G. It has only one parameter, so as only probability of success is important and number of trials is unknown. So number of trials is random here because so we don't know which one be the first successful one. And formula for the PMF is 1 minus p power k minus 1 times p, because so 1 minus p times power k minus 1 is probability of k minus 1 failures, and then it is multiplied by the probability of success. So we need for x to take value equal to k, we need k minus 1 failures followed by one single success. So probability of failure, we see power k minus 1 times probability of success. Expected value, so mean value, average value of trials we need to get the first success is 1 over p, and variance is 1 minus p over p squared.